Observe the world around you. It may not even be around you. We could be talking about what's going on inside your own body. But whether it be trees growing or refrigerators running or using your car to drive to Walmart, or the energy that's occurring inside your cells, breathing, your heart beating, chemicals dissolving, chemicals reacting, things decomposing, the wind blowing, the sun burning. All of these processes that occur in nature deal with energy transfer. And for them to happen naturally, energy has to be transferred in a certain way. And thermodynamics is the study that investigates and allows us to predict whether energy is going to be transferred in the way that allows these things to happen naturally. Scientists and thermodynamicists like to call this spontaneity, that a process is spontaneous if it happens naturally. So thermodynamics is going to give us a set of rules, a set of laws that are going to allow us to predict any process, whether it's going to be spontaneous or not. It could tell you, hey, don't waste your time trying to solve this problem because it's never, ever going to happen. It is non-spontaneous. It'll never happen naturally. Or it will happen naturally, and this is why. So it's very powerful stuff. And we're going to be using a lot of these tables. Here's a table of entropy values, a table of standard free energy, and a table of enthalpy values. And we'll be talking about these three things and how they're interrelated. Let's start with the first law of thermodynamics. Simply stated, you can never get something for nothing, or the work output can never be greater than the work input. Here's a question. According to the first law, perpetual motion machines are impossible. Then how the heck can they have one of these in the Smithsonian Museum? This is a photograph taken from this perpetual motion machine. It's this highly engineered, well-balanced machine, and it's constantly going around. Looks like it's going around all by itself. And they call it the perpetual motion machine. It's kind of misleading, though, because take a look right here. It's plugged in. There's an electrical socket. There's an electrical wire right there. So there is no such thing as a perpetual motion machine, according to the first law of thermodynamics. This first law can be written in this way. Delta, that's a delta. It also means change. So when we say delta U, we can say delta U, or change in U, equals Q plus W. So what are these variables? The change in U, or delta U, is the internal energy, the change in internal energy. Q is heat, and W is work. So what do these variables represent? Well, heat, we kind of have an understanding of heat. We know what heat is. Heat is energy, right? And that means work must also be energy. Because if you're going to add two quantities together, they have to have the same units. So work is also energy. Work is actually the transformation of energy from one form to another. Internal energy is the sum of all the forms of energy in your system. So pick a system. It could be a bottle of gas. And this gas, if you take a look at those molecules, they're vibrating, they're rotating, they're flying around in there. There's all these different modes of motion. It's translational motion, rotational motion, vibrational motion. But the point is, you add up all the different forms of energy of that system. That is the internal energy. All the forms of energy of a system. That's the internal energy. So all of them have units of joules. That's the metric unit for energy. The second law of thermodynamics. It's based on human experience. We see rocks falling. We see hot frying pans cool down. Iron rusts. A tire's punctured at high pressure and shoots out air to lower pressure. Ice melts in a warm room. What do all these things have in common? They are all spontaneous. They all happen naturally. And what's kind of important is, look, see how iron rusts? You don't see that happen in front of you. That takes years. So when these thermodynamicists say spontaneous, they don't mean right away. They don't mean the layman's way of saying spontaneous. They just mean that it's going to happen. Sooner or later, it will happen naturally. It may take generations, may take thousands of years, but it is spontaneous. It will happen. So all these processes are spontaneous, and energy is spread out. It's dispersed. Energy is spread out. Your textbook describes the second law with something like, for any spontaneous process, the entropy must always increase. So let's take a closer look at this entropy. Entropy is symbol delta S, the change in S. Does ice melt in a warm room? Sure it does. So do the cold molecules give energy to the warm air molecules, or do the warm air molecules give energy to the cold water molecules? Well, we know things always go from hot to cold, right? Energy gets dispersed. Energy gets dispersed. You have the energy is contained in that warm air molecules, and it gets dispersed to the cold water molecules. Energy gets dispersed. That's the natural way of things happening. Entropy is a measure of how spread out the energy is in a system. The third law of thermodynamics. The third law of thermodynamics. What they need is they need a baseline. They need a number we can say, hey, delta S is 0. Something that we can measure from. We need a baseline. We need a baseline. And that baseline is the third law of thermodynamics. So we can get actual numerical numbers for entropy, something that's hard to grasp. A crystal with no imperfections, and you have to be at 0 Kelvin, has an entropy of 0. So there's our baseline to measure entropy. So we can make some tables. And you'll see those tables are going to be key. Free energy and predicting spontaneity. Okay, here's the real power in thermodynamics. The change in Gibbs energy is equal to the change in enthalpy minus the temperature times the change in entropy. What do these variables represent? Well, remember, there's our Gibbs free energy. Right? Our enthalpy, our heat content. Temperature is T, and that has to be in Kelvin. And our entropy, our change in entropy. So what are their units? Well, I think you look up the tables. Usually you see kilojoules per mole for delta G. Change in enthalpy, kilojoules per mole. Temperature has to be in Kelvin. So our entropy, if we're going to use this, it needs to be in units of kilojoules per mole, but also have Kelvin denominator. So it will cancel out. And we can add kilojoules per mole, or subtract kilojoules per mole minus kilojoules per mole. When what is less than 0, the process will be spontaneous. Know this. When that Gibbs free energy. When you have negative delta G values, you know the process is going to be spontaneous. It will happen. You don't know when. You don't have any idea on the rate, but you know it will happen. How do we get numerical values for these variables? So we can use the equation to predict spontaneity for a chemical process. Tables. We'll spend some time learning how to use those tables. A reaction is more likely to be spontaneous if it is, okay, let's take a look at this. How are we going to get delta G to be as negative as possible? Okay, we want the Gibbs free energy to be negative. So we want the Gibbs free energy to be negative. A big negative number, it will even be more spontaneous. So delta H then, you'd want it to be negative, right? T is Kelvin, so T is always positive, right? You don't have any choice with that. If you want delta G to be a negative number, delta S needs to be positive, right? Because you have a positive times a positive, then you're negative in here, so that's this is the best scenario to get spontaneous processes. Make delta H negative, T positive, delta S positive. So let's see if we can answer these now. A reaction is more likely to be spontaneous if it is delta H is negative, so exothermic. The change in entropy is positive, and the reaction occurs at, make that T a huge positive number, and delta G will be even more negative. So there's different ranges of being spontaneous. The more negative delta G is, the more spontaneous that process will be, whether it's chemical or physical. Simply by looking at a reaction, how can you tell if the change in entropy will be positive or negative for that reaction? What we look for to answer a question like this is gas molecules. Look what gas molecules do. They spread out. They disperse energy very easily and very well. So you're going to have a big positive change in entropy if you produce more gas molecules. So the reactant side, you might only have a few gas molecules, but on the product side, you have more gas molecules. Let's add up those stoichiometric coefficients for the gas molecules. And delta S would be less than 0 if you have a lot of gas molecules on the reactant side, and on the product side, you have very few gas molecules, or none. So these spontaneous processes, remember you want a big positive delta S. One way to get that is to produce a lot of gas molecules in a reaction on the product side. Calculate the change in entropy for the reaction. So here's a reaction. They want us to use table 18.1. Now notice that's superscript 0. That superscript 0, that means standard. Standard values. 25 degrees Celsius, 1 atmosphere. So that means you can use the tables. So the tables are always under standard conditions. Okay? So how do you calculate the change in entropy for a reaction? Just do the sum of the entropies for all the products minus the sum of the entropies for all the reactants. That's all we do. So the change in entropy, standard, sum it all up for the products using that table, subtract out all the values for the reactants in that table, and we'll get our answer. So standard change in entropy, products. 2 of these carbon dioxide gas molecules. Here's carbon dioxide, 213.7. I have 2 of them. 2 times 213.7. And 2 water, they're liquid. Water liquid is 69.95. I have 2 of those. Okay, there's my products. Now look up the values for all the reactants. I have ethylene. There it is, 219.2, just one of them, plus 3 times oxygen. See, 3 oxygens. So oxygen gas is 205. What do I get? Okay, 2 times 213.7 plus 2 times 69.95 equals minus 219.2 plus 3 times 205, close parentheses, about negative 266.9. And what are the units? Right up here, joules per mole Kelvin. Okay, the last part was, does the entropy of the chemical system increase or decrease as you expect? Well, it decreases. It decreases. It's a negative number. So remember what we said about gas molecules. Big positive delta S when you're producing a lot of gas, and if you're not producing a lot of gas, it's going to decrease. So how many gas molecules do we have on the product side? We have 2 gas molecules. On the reactant side, we have 4 gas molecules. So as we progress from reactants to products, we're losing gas molecules. We are losing entropy then. Yes. Less gas molecules on product side. So that's what we expect. For each of the following reactions, state whether the reaction is spontaneous, non-spontaneous as written, or is easily reversible. That is, a mixture with significant amounts of reactants and products. So easily reversible just means that at equilibrium, you've got a lot of reactant left. Okay? Spontaneous means at equilibrium, you've got a lot of product, very little reactant. Non-spontaneous, you hardly have any product, and you've reached equilibrium. Everything stayed as in the form of reactants. And what you do is you look at the delta G's for that. If it's spontaneous, right, delta G is less than 0. Non-spontaneous, delta G is greater than 0. Easily reversible, delta G must be approximately 0. Okay. So we've got positive 479 kilojoules. Well, that's definitely non-spontaneous. 110 kilojoules. Again, it's positive. I'd say non-spontaneous. 2.6 kilojoules? You could argue non-spontaneous, but it's probably easily reversible because it's somewhat close to 0. Calculate the standard, well, this is superscript 0, calculate the standard change in enthalpy and the standard change in Gibbs free energy for the following reactions at 25 degrees Celsius using the tables, okay, and then interpret the signs. So let's go ahead and use our table. Here's our enthalpy table. So I'm going to calculate the standard change in enthalpy. And remember, it's just products minus reactants. So let's look up the products. I have 12 times carbon dioxide. And what is carbon dioxide gas? Enthalpy. Negative 393.5. Plus 7, plus 6 times water. 6 times water in the gaseous. Negative 241.8. Okay, there's my products minus reactants. 2 benzene 49. 2 times 49 plus 7, right? 7 oxygens, 0. So my standard change in enthalpy is going to be 12 times 393.5, it's negative, minus 6 times 241.8, minus 2 times 49. I get about negative 6270.8 kilojoules per mole. If you're not sure of the units, just look at the table. Right? The table tells you kilojoules per mole. Interpret the sign. Well, there's only 2 ways to interpret enthalpy change, and that's endothermic or exothermic. It's negative, so you'd interpret it as exothermic. It's giving off heat. Things are going to heat up. Now let's do this free energies, the standard free energies. Standard free energy, products minus reactants. 12 carbon dioxide, negative 394.4. Plus 6 times water in the gaseous form, negative 228.6. There's my products. Subtract out the reactants. 2 times benzene, C6H6 liquid, 124.4. And 7 oxygens. Oxygen gas is 0. So 12 times 394.4 negative minus 6 times 228.6 minus 2 times 124.4 equals negative 63.53. Again, the units, kilojoules per mole. There's my standard Gibbs free energy change for the reaction. And to interpret the sign, spontaneous. It's negative. So we have a couple equations that we're working with. This is the big one, though. And realize we use this equation to determine whether any process will be spontaneous or not. Just look at the sign for the Gibbs free energy.